Dry-type transformers are designed to operate with a minimum load to maintain proper cooling. When the load is too low, the transformer's magnetic core becomes saturated, resulting in increased current flow and power losses. Firstly, understand that the saturated magnetic core causes increased eddy currents and hysteresis losses, generating excessive heat. Secondly, the excessive heat can damage the transformer's insulation, windings, and other components. Thirdly, the increased magnetic flux and vibration cause the transformer to produce a loud humming noise. The best solution is to increase the load in the transformer to within its rated capacity. If increasing the load is not feasible, consider replacing the transformer with a smaller one that is more appropriate for the current load. Regularly monitor the transformer's load, temperature, and noise levels to ensure it is operating within safe limits. Since the transformer has been shut down and tired out, it is important to determine why the load on the transformer is so low. Thoroughly inspect the transformer for any damage or loose connections. Consult with the manufacturer of the transformer for guidance and support. Excessive overheating and noise from a transformer can be a safety hazard. It is important to address this issue promptly to prevent potential risks. The lack of load on the transformer is likely causing the loud humming noise and excessive heat. A dry-type transformer's minimum load is crucial for cooling. Low load leads to core saturation, which in turn increases current flow and power losses. This saturation causes increased eddy currents and hysteresis losses, ultimately generating excessive heat. Overheating damages insulation, windings, and other components. The increased magnetic flux and vibration results in a loud humming noise. The primary solution is to increase the load on the transformer to match its rated capacity. If boosting the load isn't possible, think about swapping it out for a smaller transformer suited to the existing load. Regular monitoring of the transformer's load, temperature, and noise levels ensures it's operating safely. Since the transformer has already been shut down and tagged out, the next step is to investigate the root cause of the low load. Conduct a thorough inspection of the transformer, looking for any signs of damage or loose connections. It's also advisable to contact the manufacturer for expert guidance and support. Remember, significant overheating and noise can indicate a safety hazard, and addressing the issue quickly is key to preventing potential risks. The ideal scenario is for a transformer to operate within its design parameters. When it doesn't, inefficiencies and potential dangers arise. Core saturation, caused by insufficient load, forces the core material to work harder, leading to energy dissipation in the form of heat and noise. This is not only wasteful, but also potentially destructive to the transformer's internal components. Insulation breakdown is a major concern, as it can lead to short circuits and complete transformer failure. Therefore, understanding the relationship between load and transformer health is critical for anyone managing electrical systems. When selecting a transformer, it's important to consider the expected load profile. Overspecifying the transformer can lead to the problems discussed. A slightly undersized transformer, while seemingly risky, can often operate more efficiently and reliably than a vastly oversized one operating at a fraction of its capacity. Of course, proper engineering calculations must be performed to ensure the transformer is still capable of handling peak loads without exceeding its design limits. In situations where the load is inherently variable, consider using transformers with tap changes or other load management techniques to optimize performance. These devices allow you to adjust the transformer's voltage ratio to compensate for changes in load, maintaining efficient operation across a wider range of conditions. Additionally, regular maintenance, including visual inspections and thermal monitoring, can help detect potential problems early before they escalate into major failures. Infrared thermography is a valuable tool for identifying hotspots within the transformer, indicating areas of excessive heat and potential insulation breakdown. These periodic checks can save significant costs in the long run by preventing costly repairs and downtime. Transformers are robust pieces of equipment when used correctly, but ignoring their design limitations can lead to significant problems. Pay attention to the load, monitor their condition, and take proactive steps to address any issues that arise. By understanding the principles of transformer operation and implementing proper maintenance practices, you can ensure their reliable and efficient performance for many years to come. The core of a transformer is typically made of laminated silicon steel. These laminations are designed to reduce eddy current losses, but they are not perfect. When the core saturates, it behaves like a solid piece of metal, dramatically increasing eddy current losses and heat generation. Hysteresis loss is also increased due to the nonlinear magnetic behavior of the saturated core. Hysteresis is the energy lost as the magnetic domains within the core material realign themselves during each alternating current cycle. Core saturation makes this process more difficult and energy intensive. The humming noise is caused by magnetostriction, which is the tendency of ferromagnetic materials to change their shape or dimensions during magnetization. The alternating magnetic field causes the core to vibrate, producing the characteristic humming sound. When the core is saturated, the magnetostriction effect is amplified, resulting in a louder and more noticeable hum. To mitigate the risks associated with low load operation, consider implementing load shedding techniques. This involves temporarily disconnecting non-essential loads to increase the overall load in the transformer. This can be done manually or automatically using a load management system. Another option is to use multiple smaller transformers instead of one large transformer. This allows you to switch transformers on or off as needed to match the load, improving efficiency and reducing the risk of core saturation. Solid-state transformers are also becoming increasingly popular. These transformers use power electronic converters to perform the voltage transformation, eliminating the need for a magnetic core. This makes them smaller, lighter, and more efficient than traditional transformers, especially at low loads. When inspecting a transformer, look for signs of overheating, such as discolored paint, bulging, or cracked insulation, and the smell of burning. Also, check for loose connections, damaged wiring, and any signs of physical damage. Use a thermal camera to identify hotspots on the transformer's surface. A significant temperature difference between different parts of the transformer can indicate a problem. Consult the transformer's nameplate for its rated voltage, current, and kVAR. Ensure that the actual load is within the transformer's rated capacity. Also, check the transformer's impedance. A higher impedance transformer will have lower fault current, but it will also have a higher voltage drop under load. When contacting the manufacturer, provide them with as much information as possible about the transformer, including its serial number, model number, and operating conditions. This will help them to diagnose the problem and provide appropriate recommendations. Transformer oil, if applicable, should be tested regularly to ensure that it is free of contaminants and that it is still providing adequate insulation and cooling. Oil testing can reveal problems such as moisture contamination, oxidation, and the presence of dissolved gases, which can indicate internal faults. Proper grounding is essential for transformer safety. Ensure that the transformer is properly grounded to prevent electric shock and to protect against lightning strikes. The grounding system should be inspected regularly to ensure that it is in good condition. Lightning arresters can also be used to protect the transformer from voltage surges caused by lightning. These devices divert the surge current to ground, preventing it from damaging the transformer. Consider installing a transformer monitoring system. These systems continuously monitor the transformer's voltage, current, temperature, and other parameters, providing early warning of potential problems. The data can be used to optimize transformer performance and to prevent failures. If the transformer is located in a harsh environment, such as a dusty or corrosive atmosphere, take steps to protect it from the elements. This may involve installing a protective enclosure or using a transformer with a special coating. Regular cleaning can also help to prevent the buildup of dirt and debris, which can reduce cooling efficiency. Transformers are essential components of electrical power systems, providing reliable and efficient voltage transformation. By understanding their operating principles and implementing proper maintenance practices, we can ensure their continued performance and prevent costly failures. Transformers are rated in kV, which stands for kilovolt amperes. This is a measure of the transformer's apparent power, which is the product of voltage and current. The actual power delivered by the transformer depends on the power factor of the load. The power factor is a measure of how effectively the electrical power is being used. A power factor of 1.0 indicates that the voltage and current are in phase and that all of the power is being used to do work. A power factor of less than 1.0 indicates that the voltage and current are out of phase and that some of the power is being wasted. Transformers are typically designed to operate at a power factor of 0.8 or higher. If the power factor is too low, the transformer may overheat and fail. Power factor correction can be used to improve the power factor of the load. This involves adding capacitors to the circuit to compensate for the inductive reactance of the load. The capacitors store energy and release it back into the circuit, reducing the phase difference between the voltage and current. This improves the power factor and reduces the amount of current that the transformer has to deliver. There are several different types of dry-type transformers, each with its own advantages and disadvantages. Ventilated transformers are the most common type. They have openings in the enclosure to allow for air circulation, which helps to cool the transformer. However, they are also more susceptible to contamination from dust and moisture. Encapsulated transformers have their windings completely encapsulated in resin, which protects them from dust, moisture, and corrosive atmospheres. They are more expensive than ventilated transformers, but they are also more durable and reliable. Non-ventilated transformers are completely sealed and do not require any ventilation. They are used in applications where dust, moisture, or corrosive atmospheres are a concern. They are the most expensive type of dry-type transformer. The choice of transformer type depends on the specific application and the environmental conditions. In some cases, it may be necessary to use a special type of transformer, such as a K-factor transformer, which is designed to handle nonlinear loads. Nonlinear loads, such as computers and electronic equipment, generate harmonic currents, which can overheat transformers. K-factor transformers are designed to withstand these harmonic currents without overheating. It is important to choose the right type of transformer for the application to ensure reliable and efficient operation. Transformers are static devices that convert alternating current electricity from one voltage to another through electromagnetic induction. They are a fundamental component of any electrical grid, enabling the efficient transmission and distribution of power over long distances. A transformer consists of two or more coils of wire, electrically isolated but magnetically linked. The coils are wound around a common iron core, which enhances the magnetic field and improves the transformer's efficiency. The primary winding is connected to the input voltage source, while the secondary winding is connected to the load. When alternating current flows through the primary winding, it creates a magnetic field that induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. A step-up transformer has more turns in the secondary winding than in the primary winding, resulting in a higher output voltage. A step-down transformer has fewer turns in the secondary winding than in the primary winding, resulting in a lower output voltage. The power in the primary winding is equal to a power in the secondary winding, assuming ideal conditions. In reality, there are always some losses due to factors such as coil losses, winding resistance, and leakage flux. Transformers are used in a wide variety of applications, including power generation, transmission, distribution, and utilization. They are also used in electronic devices such as power supplies and audio amplifiers. Transformers are essential for modern electrical systems, providing a safe and efficient means of voltage transformation. In summary, transformers are essential components in electrical systems, and understanding their operation is crucial for ensuring their reliability and longevity.